So here's something that hopefully everybody remembers from elementary school. Yeah, grade 3 is a prerequisite for this course, so you need to know this. Okay, this is probably not how it was written in elementary school, but let n and k be integers where k is not 0. So when n is divided by k, there is a unique quotient and remainder. Maybe, yeah, they probably didn't present this to you in this way in elementary school, but this was kind of a fact, right, that everyone kind of assumed, right? When I take a number and I divide it by another number, it goes into that number a certain number of times, and then there's a remainder, and the answer is unique, right? You can't divide it in two different ways and get two different answers. The teacher marks it yes, correct or not. There's no second possible answer. So, for example, let's say n is 65. Let's say k is 17. So, okay, how many times does 17 go into 65? I guess, one way to do it, you can kind of just say, okay, 1 times 17 is 17. That's not going to be, it's not very close to 65. 2 times 17 is 34. 3 times 17 is 51. If I do 4 times 17, that's 68. That's too big. So 17 does not go into 65 4 times. So I need to, basically my quotient, when I divide 65 by 17, the quotient is 3. It goes in 3 times. And my remainder is going to be whatever 65 minus 51 is, so it's 14. So 65 is 3 times 17 plus 14. This is my quotient, and this is the remainder. And one kind of fact is that, so when you divide n by k, the remainder, well, you can have a remainder of 0, right? Or 1 or 2. You can't have a remainder of k or bigger, right? Because if the remainder was like k or k plus 1 or something, I would just take out another k. So the remainder is between 0 and k minus 1. So does this kind of feel familiar, right? Do you see why this is true? So if your remainder was, if you were trying to divide, basically, for example, when I get to 2 times 17, if I tried to do a remainder right now, it would be 31. But 31 is bigger than 17, so I can take out another 17. So as long as your remainder is bigger than k, you can keep taking out more k's, right? So it should be between 0 and k minus 1. So let me actually write a theorem here. So this is something we'll call the Division Theorem. So let n and k be integers with k being non-zero. We always have to take k to be non-zero because you can't divide by 0, basically. So then there exist unique integers q and r such that n can be written as q times k plus r. And so this is an important part. R is between 0 and the absolute value of k minus 1. So the letters q and r are chosen, to give you a sort of signal. Q is the quotient, r is the remainder, right? But this is just telling you something that you've implicitly known for a very long time, right? When someone asks you to divide n by k with figure out the quotient and remainder, there's always a unique answer. You can't have two people getting two different answers that are both correct, right? There's only one answer. So this is all this is saying. Maybe the weird thing about this, though, is you can have n and k being negative. And so let's look at some examples like that. So for example, let's take n equal to 77, k equal to negative 10. So yeah, this is a little bit weird, right? How many times does negative 10 go into 77? Yeah, should be something like that. I think that's going to be correct. Yeah, negative 7, because yeah. So if I take 77 So suppose I just start by writing, like, so pretty much you can kind of tell in this example, the answer is either going to be -7 or -8, because, I mean, those are the closest kind of, if I take 77 over -10, the closest numbers are -7 or -8. You just have to figure out which one's right. So let's try -7. So what would be my remainder here? I think so, yeah, +7. And now you know that this is right because 7 is between 0 and absolute value of -10 minus 1, which is 9. So as long as your remainder is between the right numbers, like if it's positive and not too big, you know that you've done it right, because, yeah. So here's one thing that could trip you up, right? So it would be wrong if I wrote, well, okay, so this is my quotient. This is my remainder, right? If I wrote this as -8, like, okay, this is true, but the problem is if I was asking for the quotient and remainder, this is negative, and that's bad, right? Our remainders are not supposed to be negative. Okay, so another example. So let's say, maybe this is an even easier example. So n is -54, k is 6. This is kind of easier, right? Because it's just, your quotient is just -9, and then the remainder is 0. So remember when we were doing this example, what I said was, like, pretty much, if you think about it, the only sensible answers for the quotient are like -7 or -8, right? There's no way it's going to be something else, Basically, if you take n divided by k, and you look at the closest integers, one of those is going to be correct for the quotient. And that's a general fact. So let me just say a bit more about that. So I need a bit of notation. So given a real number x, the floor of x is the largest integer such that that integer is at most x. Okay, and the notation for this, so the floor of x is written like this. This might sound kind of technical, but all I'm saying here is round it down, right? So the floor of x is just, round x down to the nearest integer, right? So it's the biggest integer that's less than or equal to x, but that's just like, you just round it down. The ceiling of x is kind of the similar thing, right? You just round it up. So it's the minimum integer, m and z, such that x is at most m. And here the notation is basically the same, but like this. And so, I mean, really, this is just saying round x up. So if this formal definition is hard to kind of understand, I think you can probably understand it with a few examples. So if I take 3.12 and I take the floor, well, that's just 3, right? It's the biggest integer, which is at most 3.12. So it's, yeah, rounded down. If I take 3.12, I take the ceiling, that's 4. Now, if I take an actual integer, like 7, and I take the ceiling, well, I always get 7. And if I take the floor, I get 7 as well. So if you take basically, if I take an actual integer and I try to round it up, well, it's already rounded. So you don't need to, or you try to round it down, it's already an integer. So it doesn't do anything. Slightly sneaky example is, what if I take the floor of -2.5? If you're just kind of not really thinking and you're doing things quickly, you could miss that, right? Because kind of feels like it might be -2, because you might think, oh, I'm going to round down 2.5 to 2, but it's not -2. It's that's correct. It's -3. And similarly, the ceiling is -2, right? Because that's the smallest integer, which is bigger than -2.5. So how does this connect to this quotient and remainder stuff? Well, the way it connects is that, so if you divide n by k, is always, well, sometimes it's, so it's always going to be the floor of n over k or the ceiling of n over k, like I said. So, right, because if you think about it, remember the 77 divided by -10, we said the only real possible answers are -7 or -8, right? Which is the floor or the ceiling. It turns out that it's equal to this if k is positive, and it's the floor if k is positive, and it's the ceiling if k is negative. Of course, you don't have to memorize this. You can just, in every case, you can just work it out, but this might give you a quicker way of doing it, right? If k is positive, you just compute the floor of n over k. Like, for example, you could just put n over k in your calculator, right, if you've got one, and then just like round that down, Okay, so what I want to talk about now is changing bases. So what do I mean by that? So here's a fact. Our number system that we use all the time is base 10, right? So in other words, there's 10 different symbols. So 0, 1, 2, up to 9, right? That's what it means to be base 10. We use 10 different symbols to create numbers, right? If you think about how base 10 works, so what really is the number 5,294? Okay, well, it's the number 5,294. But if we think of how we really construct this, so what this means, what this writing these numbers beside each other really means is that we take we take 5,000s. 1,000 is 10 to the 3. To that, to 5,000, we add 200s. So 2 times 10 to the 2, 9 times 10 to the 1, and then we're left with 4, which is 4 times 10 to the 0, because 10 to the 0 is 1, right? Anything to the 0 is 1. So what we're going to focus on for probably most of the rest of the lecture is how do suppose I don't want to write things in base 10, but I want to write it with a different base. So what does that really mean? So how are you familiar with binary? How many people are familiar with, that's how computers talk, right? Binary. So yeah, so we can also write numbers, with different bases. So base 2 would be binary, right? But we could also pick anything else, right? We could do things base 37 if we really wanted to. Or base 16. So that's something called hexadecimal. As far as I know, base 37 doesn't have a name, but we can do it with respect to any base. Okay. So what do I mean by that? So when I wrote this thing, so the point here is that when you write things in base 10, you've got powers of 10 with coefficients which are between 0 and 9, right? So the coefficients are always 0, 1, 2, up to 9. Right? That's how you write a number. You basically, in each spot, you put a number which is 0, 1, 2, up to 9. So to write things in base B, base B, where B is some, so let's say B is just some integer, which is at least 2. So to write n in base B, you write n is equal to some coefficient, which I'll call dk, b to the k, dk minus 1, b to the k minus 1, plus dot, 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 d2 b squared, d1 times b to the 1, plus d0 times b to the 0. So in other words, you want to write it in terms of powers of b. So instead of powers of 10, where the coefficients are in, so this is always going to be a number between 0 and b minus 1. So hopefully that seems kind of analogous, right? I had powers of 10. Those become powers of b. I had coefficients between 0 and 9. That becomes coefficients between 0 and b minus 1. Because base 10, it's between 0 and 9. Base b, it's between 0 and b minus 1. So let's go right into an example, actually. So I'm going to write 68 in base 5. So I'm going to write 68 equals something of this form where b is equal to 5. So here's a question. What's the biggest? So, we want to write it with powers of 5, right? What's the biggest power of 5 that I should use here? So 5 to the 0, or 5 to the 1, or 5 to the 2, or 5 to the 3, 4, etc. 2. How come?
5 to the power of 3 is 125.
Yeah, exactly. So we're going to start with, so I'm going to write this as d2, 5 squared, plus d1 times 5 to the 1, plus d0, 5 to the 0. And, we start with 5 squared because 5 to the 5 cubed is 125, which is too big, right? So there's no way we can actually use that, right? Yeah, good. So here's the trick. So what I'm going to do is I'm going to actually, so I want to figure out what these coefficients are, right? Like I haven't done anything yet. I need to figure out what these numbers are. Here's a way you can do it. So if I take out, suppose so I'm going to take out a 5 from these two terms. And I'm going to notice that 5 to the 0 is 1, so I can just write d0 here. Now this should look kind of familiar with what we were doing earlier. So what is d0 now? Exactly, yeah, right? Because we're trying to find a number between 0 and 4, which has the property that 68 is equal to this thing times 5 plus that number. The remainder is unique, right? So, I mean, this looks like the remainder when I divide by 5. So d naught is the remainder when 68 is divided by 5. So therefore, d naught, d0 is 3, right? Because really, we've written 68 as some integer times 5 plus d naught. So, and d naught is between 0 and 5 minus 1, so it has to be the remainder. There's no other choice. The remainder is unique. Okay. So now we can use that to help us get the next number. Right? Because if I take, so now if I write down my 68 is d2 times 5 plus d1 plus, times 5 plus 3. So I've determined this 3. I can now move the 3 to the other side and divide by 5. So 68 minus 3 over 5, which is 13, is equal to d2 times 5 plus d1. So now what's d1? That's the remainder when I divide 13 by 5, right? So, which is again 3. So d1 is 3 as well. And then you can see pretty easily here, d2 is going to be 2. But we can also, we can again do the, bringing things around and dividing by 5. So if I take 13 minus 3 over 5, which is 2, that's going to be equal to d2. So d2 is 2. So therefore 68 is 2 times 5 squared plus 3 times 5 plus 3, so 5 to the 1 times 3 times 5 to the 0. Or plus, yeah. Okay, so that's my base 5 representation of 68. Now the notation we're going to use for this is to say that, so 68 in base 10 is equal to 233 in base 5. So we just take these coefficients here and we write them like this. Okay. So the subscript here tells you what the base is. Any questions about that? One thing is you got to remember to write these in the correct order. So it's not, so you don't, the first thing I worked out was this 3, and then I worked out that 3, and then that 2. But I write them down 2, 3, 3, like this. But yeah. Any questions? So generally, if n is equal to dk b to the k, dk minus 1, b to the k minus 1, plus dot, 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 d1 b to the 1, d0 b to the 0. Then we write that n is dk minus 1, dot, 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 d1 d0 base b, in base b, I guess. Okay. So here's a weird question, though. What if this worked out kind of nicely because the base is 5. So we're going to use numbers between 0 and 4. What if the base is bigger than 10? That becomes a little bit awkward. So if the base b is bigger than 10, one option is to for how to represent your numbers is to define more symbols. More symbols to represent the numbers between, let's say x between 10 and b. Okay, so, doing it this way is kind of fine if you wanted to just write an 11 there, but we could also just say, let the number 11 be the symbol smiley face or something, and then we draw a smiley face instead, right? So one example, which actually people use in, various, computer-y things is hexadecimal, so which is base 16. So in hexadecimal, the numbers 0 up to 9 are just the usual 0 up to 9, and they define A to be 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So then your number system is the number 0, 1 up to 9, and then A up to F. Right? And there's 16 different numbers. Right? So this gets around this whole issue of writing 2-digit numbers, right? So we just, instead of writing the number 12, you just write a C. Yeah, yeah. Now, of course, eventually you'll run out of numbers too. If you go to base 100, then you don't have enough, but you just start making up symbols, right? Squiggly things or smiley faces. It's not very practical, to be honest, to deal with base 100, but you could do it in principle. Yeah, use Greek letters, use Chinese characters, use whatever you want, you know, like, you know, use Korean, use, yeah, whatever alphabet you want, basically. Okay, so just a quick example with hexadecimal. So if we define our symbols in this way, then if I take, let's say, 8AF 16, base 16, you know, so what is this in base 10? So I won't be able to do this in one step, but there's a bit of a calculation here. So how would I start this calculation? I'm not sure if it's clear what I mean by that, but yeah. Yeah, you may as well do that. That's a good idea. Yeah. Right, so this has 3 digits. Or 3, I mean, they're not exactly digits anymore. They're kind of hexadecimal digits anyway. So, right, so you're going to have something to the 0, something to the 1, something to the 2. And then you just fill in your numbers, right? So 8 is just 8, so that's an 8. A means 10, so that should be 10. F means 15, so that should be 15. Which is apparently 2, 2, 2, 3, if you just do the calculation. Okay. Any questions about that? Okay. It's pretty easy, I think, to go in this direction, right? If you're given something with some weird base, to get it to base 10, you do just you just write this out and do the calculation. Going from base 10 to base 16 is a bit trickier, but we had a method for doing that last time, right? You take your 2, 2, 2, 3, you say, what is the remainder when it's divided by 16? It'll be 15, so you write that down, and then you kind of work it out step by step.